This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So today we are going to discuss the branching instructions of 8051 microcontroller in microprocessor and microcontroller course. The slides are prepared by referring the textbook, the 8051 microcontroller by Kenneth J. Ayala, publication Cengage Learning. In 8051 microcontroller, the various instructions which are existing are broadly classified into data transfer instructions, arithmetic instructions, logical instructions, branch instructions, subroutine instruction, and bit manipulation instruction. Under this, today we are going to see the branch instruction as well as subroutine instructions. So the branch instruction means the control will be transferred from the current execution to another location. Either the new location may be in the same program or it may be a different program. In branch instructions, there are mainly two kinds of branch instructions are there. One is unconditional jump instructions or unconditional control transfer instructions. The second category is conditional control transfer instructions or conditional jump instructions. The unconditional jump instructions, upon their execution, a jump to a new location from where the program continuous execution is executed. In conditional jump instruction, a jump to a new program location is executed only if a specified condition is met. Otherwise, the program normally proceed with the next instruction. The mnemonics associated with branch transfer instructions are given below. JMP unconditional jump, JC jump if carry, JNC jump if no carry, DJNZ jump decrement and jump if no zero, CJNE compare and jump if not equal, JNZ jump if not zero, JZ jump if 0, SJMP short jump, LJMP long jump, AJMP absolute jump, LCall that is long call, ACall absolute call, RET return, RETI return from ISR, JB jump if bit, JNB jump if no bit, JBC jump if bit and clear. The first instruction under this category is JMP instruction, which is a unconditional jump. So this instruction will jump to a address which is pointed by a data pointer and accumulator. The jump instruction jump unconditional to the address represented by the sum of the values of a DPTR register, that is a data pointer register, and the value of the accumulator. This instruction add the 8-bit unsigned value of the accumulator to the 16-bit data pointer, and the resulting sum is returned to the PC. Neither accumulator nor a data pointer will be altered after executing this instruction. The syntax of the instruction is JMP @A plus DPTR. So it is for indirect way of mentioning the address. So the address will be calculated by the addition of accumulator contents with the DPTR register contents. So if we have a program, let us consider few instructions we are having. Somewhere here we will write a jump instruction. When this jump instruction is executed, the control may be transferred to the previous instructions or the next instructions which are followed by the jump instructions. So Depending upon the address which is pointed by the addition of accumulator contents with the DPTR, the new location will be fetched. The next instruction is JC, jump if carry set. The JC instruction branch to the address indicated by the relative address in the instruction if the carry bit is set. If the carry bit is not set, the program execution continues with the instruction following the JC instruction. Suppose we have few instructions like I1, IN2, then we will write JC, some relative address is L1, then I have instruction 3, instruction 4 at L1, then I will write instruction 5, instruction 6 like this. Let us assume few instructions we are having like this. So here first the IN1 is executed, then the second instruction will be executed. Depending upon the result which are obtained after instruction 2, if carry flag is equivalent to 1, the possibility is either the carry flag may be 1 or the carry flag may be 0. If the carry flag is 1, it is the true case for JC. So immediately the control will be transferred to label 1. If, let us consider, if carry flag is equivalent to 0, the condition is fails, so the control will not be transferred to label 1. This next instruction which we are having here, that will be executed. So if the carry flag is equivalent to 1, the control will be transferred to L1. If the carry flag is equivalent to 0, the control will be transferred to the instruction 3 in this example. The syntax of the instruction is a JC, a relative address. Example, JC L1. So L1 is a label which you are specifying for some memory location. The next instruction is JNC, which is jump if carry not set. The JNC instruction branch to the address indicated by the relative address if the carry bit is not set. If the carry bit is set, program execution continues with the instruction following the JNC instruction. The syntax of the instruction is JNC relative address. Here also we will take the example. Let us consider we have the instructions are instruction 1, instruction 2. After that we have the instruction is JNC, some label 1. Next we have instruction 3, instruction 4. For instruction 5, assume label 1 is specified. Then we have instruction 6. First IN1, instruction 1 will be executed. Then instruction 2 will be executed. Upon the execution of instruction 2, if the carry flag is equivalent to 1 or 0, the control transfer will be changes. If the carry flag is equivalent to 1 after executing the instruction 2, as we are checking for no carry and this is a carry 1 which is a false case, so IN3 will be executed. Suppose if after IN2 execution, if the carry flag is equivalent to 0, in that case the condition is true, so that is jump if no carry, the control will be transferred to the label 1 which was specified. Immediately the control will be transferred to the label 1 where we have the instruction 5. This will be executed. The syntax of the instruction is JNC L1, where L1 is the address of a particular memory location where we want to transfer the control if carry flag is equivalent to 0. The next instruction is DJNZ, which is decrement and jump if not 0. The DJNZ instruction decrement the value of the register by 1. If the initial value of the register is 0, after decrementing the value is FF in hexadecimal, which is equivalent to 255 in decimal. So if the new address value of the register is not 0, the program will be branched to the address indicated by the relative address in the instruction. If the new value of the register is 0, a program continues with the instructions followed by DJNZ instruction. The syntax of the instruction is DJNZ a register, comma, relative address. Otherwise, we can have the operands. One is either the decrement will be takes place with the register contents or with the direct memory address only. DJNZ direct, comma, relative address. Example, DJNZ R0, comma, L1. Second example, DJNZ 40H, comma, L1. So the first one is R0 we are going to check. So here When you are executing this instruction, first R0 will be decremented by 1. After decrementing it, then we will check for whether this R0 is non-zero or not. If it is non-zero, then go to label 1. Else, that means if R0 contents are equivalent to 0, then the next instruction will be executed. Similarly, for the second one, where the contents of the memory at memory address 40H will be checked. That is for decremented. Then it will check for whether it is non-zero or not. If it is non-zero, go to label 1. Otherwise, subsequent instruction will be executed. The next instruction is CJNE, compare and jump if not equal. The CJNE instruction compares the value of the operand 1 and operand 2 and branches to the indicated relative address if operand 1 and operand 2 are not equal. If the two operands are equal, program flows continuous with the subsequent instruction, that is following CJNE instruction. The syntax of the instruction is CJNE operand 1, operand 2, then relative address. Example, CJNE R3, hash 50H, L1. So here the microcontroller will check whether the content of R3 is equivalent to 50H or not. If it is 50H, the next instruction will be executed because the condition is fails, which we are checking for is not equality. If R3 content is equivalent to 50H, if R3 contents are not equivalent to 50H, then the control will be transferred to label 1 because the condition which you are checking is not equal. The next instruction is JZ, which is jump if accumulator is 0. The JZ instruction branches to the address indicated by the relative address in the instruction if the accumulator contains the value is 0. If the accumulator content is non-zero, the program execution continues with the instruction following the JZ instruction. The syntax of the instruction is a JZ relative address. Example, JZ L1. So here let us consider we have instruction 1, instruction 2, then we will write a JZ sum L1, then I have instruction 3, instruction 4. For L1 we will have L5, instruction 5 and instruction 6. So when this instruction is encountered after executing IN1 and IN2, then it will check for whether the accumulator content is 0 or accumulator content is non-zero. What is the true case for here? It is jump if 0. That means if accumulator content is 0, then go to label 1. Otherwise, go to the subsequent instruction, which is nothing but IN3 in this example. The next instruction is JNZ, which is jump if accumulator not 0. The JNZ instruction branches to the address indicated by the relative address if the accumulator contains the value is not 0. If the value of the accumulator is 0, program execution continues with the instruction following the JNZ instruction. The syntax of the instruction is JNZ relative address. Example is JNZ L1. So here also let us assume we have the instructions are instruction 1, instruction 2, then we wrote JNZ L1, then I have instruction 3, instruction 4 at L1, then we have instruction 5 and instruction 6. So after executing instruction 1 and instruction 2, then it will check for JNZ. So here what is the value it is going to check is if accumulator content is equivalent to 0 and accumulator content is non-zero. If the accumulator content is 0, the condition is false, so go to the execution of instruction 3. If the accumulator content is non-zero, then go to label 1. The next instruction is SJump, which is short jump. This is also unconditional jump instruction only. In previous JMP instruction, where the address we are going to be specify with the accumulator and the DPTR. When it comes to SJMP, the address we can specify in the instruction. So the SJMP instruction jumps unconditional to the address specified in the relative address the relative address must be within minus 128 or plus 127 bytes of the instruction that follows sjump instruction. So somewhere here we have sjump L1 we have placed. Then this control L1 we can place in the upward direction, that means the previous instructions which are executed with a displacement of up to minus 128 locations. In the downside, the control may be transferred until 127 location. So here for sjump, the relative address which it is going to have the span is minus 128 to plus 127, which is having a width of 256 location. So this relative address which we are going to be specified having a width of 8-bit size. The syntax of the instruction is sjump L1. The next instruction is ljump, which is a long jump. The long jump instruction is also unconditional jump instruction. The only variation between sjump and ljump is how much displacement it can be takes place. The ljump instruction jumps unconditionally to the specified code address. Here, whatever the code address which you are going to be specified, that we can have a 16-bit white space. The syntax of the instruction is sjump, the address which is of 16-bit size we have to represent. Example, ljmp L1. So here also till 2000 to the power of 15, that many number of combination locations we can have. So this 15-bit width upward side as well as in the downward side we can have. That is 32K in the upward, 32K in the downward side, including 0. The next instruction is ajump, where ajump is absolute jump. Here, the difference between sjump, ljump, ajump is how much displacement you are representing. For ajump, we are going to be representing the displacement is 11-bit size. So where it can jump within the 2K block, 1K above, 1K downward we can take. The ajump instruction is a unconditional jump to the indicated code address. The new value for the program counter is calculated by replacing the least significant bits of the PC with the second byte of the ajump instruction and replacing bits 0 to 2 of the most significant byte of the program counter with the 3 bits that indicates the page of the byte following the jump instruction. Bit 3 to 7 of the most significant byte of the program counter remain unchanged. Since only 11 bits of the program counter are affected by ajump, jump to the code location within the same 2K location as the first byte that follows the ajump instruction. The syntax of the instruction is ajump, the address which you are going to be specified is 11-bit size. The next instruction is lcall, which is long call. This call instruction is used for transferring the control from one program to another program. Lcall instruction calls a program, that is a subroutine. Lcall increments the program counter by 3, that is to point the instruction following the lcall and pushes the value of the program counter, that is PC, onto the top of the stack. When we are placing onto the top of the stack, first lower byte will be placed, then higher byte will be placed. The program counter is then set to the 16-bit value which follows the lcall opcode, causing program to execute continuous at that particular address. Syntax of the instruction is lcall, code address is 16-bit size. So here, let us assume this is one program. This I am taking as a main program, and here we have a subroutine. When we are executing the instructions, instruction 1, instruction 2, let us consider we have encounter the lcall instruction. Well, lcall instruction is encounter. Whatever the address of the next instruction to be executed after lcall will be moved onto the top of the stack. Then the address of this subroutine, this will be loaded into the program counter. Then the control will be transferred from the main program to the subroutine. After executing the entire subroutine, again we will move back to main program. So in the L call, the displacement which you can specify the address of the subroutine with a 16-bit address. The next one is L call. After that we have A call, where A call stands for absolute call, but the main program, that is calling program and call program, should reside within the 2K block. The A call instruction unconditional calls a subroutine. A call instruction pushes the address of the instruction that follows A call onto the top of the stack. When you are placing the contents onto the top of the stack, first a least significant byte is placed, then most significant byte will be placed. The program counter is then updated so that the program execution continues with the indicated address. This address which we are going to be loaded, which is nothing but it is the address of the subroutine. The new value of the program counter is calculated by replacing the least significant byte of the program counter with the second byte of the A call instruction and replacing the bits 0 to 2 of the most significant byte of the program counter with 3 bits that indicates the page. In this bit 3 to 7 of the most significant byte of the program counter remains unchanged because we are taking only 11 bits. The upper 3 to 7 bits will be remains same. Since only 11 bits of the program counter are affected by A call, many only the program routine, that is subroutine, located within the 2K block as the first byte that follows the A call. The syntax of the instruction is A call address, which is of 11-bit size. Example, A call timer init. So where timer init is initialization, it is a subroutine. So under call instructions, we have studied two instructions. One is L call, the second one is A call. These two instructions are used for to call a subroutine. Subroutine is nothing but another program. Let us assume this is what my main program from where I am calling the subroutine. The difference between L call and A call is whatever the address which you are going to be specified for this particular subroutine, you can have a bit width of a 16-bit size maximum. When it comes to A call, the size of this address should be vary from this one to here only by 11 bits. That is the major difference between a L call and A call. Both are used for calling a subroutine, but the subroutine location where it has to be exist, whether within the 2K block or outside of it. Depending upon that, we are going to use L call or A call instruction. The next instruction is RET instruction. It is for return from a subroutine. So when a call instruction, either it may be L call or A call, when this instruction is encountered, the control is transferred from main program to subroutine. When the subroutine is executing, the controller will know the end of this particular subroutine by using RET instruction. So the RET instruction should be written as the last instruction in a subroutine. Whenever the microcontroller encounters this RET instruction, immediately the control will be transferred to the main program. So to which location it has to be sent from subroutine to main program is, so when the call instruction is taking place, on the top of the stacks already the instruction address we are going to be loaded in the top of the stack. When the control is transferring from return to the main program, this top of the stack contents will be loaded into this. The RET instruction is used to return from a subroutine previously called by a call instruction, either it may be a L call or absolute call. The program continues at that address is calculated by popping the most 2 bytes of the stack, which is nothing but top of the stack contents. The most significant byte is popped off the stack first, following the least significant byte. So when we are moving from L call to, that is main program, to subroutine onto the top of the stack, first we are loaded with a lower byte, on the top of that we are placed higher byte. When we are popping out, first higher byte will be fetched, then lower byte will be fetched. The syntax of the instruction is RET instruction, which will not have any operand. So it is simple RET instruction indicating written from a routine, subroutine. So RET instruction should be always the last instruction in a subroutine. Suppose in a subroutine, we are not written RET instruction, what will happen? So the program, whatever it is consist from the location which was specified for the subroutine, from that point till RET is encountered, the microcontroller will treat that this is a entire program corresponding to the subroutine which we are called. So RET instruction compulsorily we have to write as a last instruction in the subroutine. The next instruction is RETI, which is written from interrupt subroutine. The RETI instruction is used to return from a interrupt subroutine or service routine. RET instruction we are writing as a last instruction for normal subroutine, whereas RETI we will write as a last instruction for a subroutine which is corresponding to a particular interrupt, that is interrupt service routine. RETI first enables the interrupts of equal and lower priorities to the interrupt that is terminating. Program execution continues at the address is calculated by the popping the topmost two locations of the stack, that is nothing but top of the stack. The most significant byte is popped first from the stack and followed by the least significant byte. The syntax of the instruction is RETI. The next instruction is JB, which is jump if byte set. The JB instruction branches to the address indicated by the relative address if the bit indicated by the bit address is set. If the bit is not set, program execution continues with the instruction following the JB instruction. So this JB instruction is also like a conditional control transfer instruction. So the syntax of the instruction is JB, bit address will feature, comma, relative address we can have. So let us consider, we will write a JB PSW.7 array 1. So array 1 is the address for one location we are giving. So when we are going to go to the address 1 is, if the program status word 7th bit is equivalent to 1, then go to the label that is array 1. Suppose if PSW.7 is equivalent to 0, then go to the next instruction followed by JB instruction. Similarly for the second example, which is JB P1.2 array 2. So here what is the condition it is going to check is whether the port 1 second bit is equivalent to 1 or 0. If it is 1, go to array 2. If port 1.2 is equivalent to 0, then go to the next instruction. The next instruction is JNB instruction, which is jump if bit not set. The JNB instruction branches to the address indicated by the relative address if the indicated bit is not set. If the bit is set, the program continues with the instruction following the JNB instruction. The syntax of the instruction is JNB a bit, comma, relative address. So let us consider, we will take a JNB PSW.7, comma, array 1 as one example. The second example is JNB P1.2, comma, array 2. So here the value which you are going to be check is program status word, the 7th bit. If it is equivalent to 0, then go to array 1. Suppose if the program status word 7th bit is equivalent to 1, then go to the next instruction. Similarly for JNB, which is for checking the port 1 second bit. So if port 1 second bit is equivalent to 1, then go to array 2. Suppose if port 1 second bit is equivalent to 0, then go to the next instruction followed by the JNB instruction. The third instruction is JBC, which is jump if bit set and clear the bit. The JBC instruction branches to the address indicated by the relative address if the bit is indicated by the bit address is set. Before branching to the relative address, the instruction will clear the indicated bit. If the bit is not set, program execution continues with the instruction following the JBC instruction. The syntax of the instruction is JBC bit address comma relative address. Example, JBC the program status word dot 7 comma array 1. So what this instruction will do is, first it will check if the program status word 0.7 is equivalent to 1, then go to array 1, but before going to array 1, here clear the corresponding bit, that is PSW dot 7 bit will be cleared before the control is transferring to the array 1. Similarly, JBC P1.2 comma array 2, here it will check whether the P1.2 is equivalent to 1 or not. If it is 1, go to array 2, but before going to array 2, here we are going to clear the port 1.2 bit. Suppose if P1.2 is equivalent to 0, then it is going to execute the next instruction followed by JBC instruction. Similarly for first example also. So in this session, we have discussed the various branch or control transfer instructions which are supported in 8051 microcontroller. Mainly we have discussed JMP instruction, then SJump instruction, LJump instruction, AJump instruction. The JMP instruction is an unconditional jump where control has to be transferred will be indicated by the accumulator and DPTR. Whereas for SJump or AJump or LJump, the relative address will be specified in the instruction. In the SJump, the displacement is only 8 bit size, that is minus 128 to plus 127 location. If it is absolute jump, the displacement is 11 bits. If it is a long jump, then the relative address is 16 bit size. Then we have discussed jump if carry, jump if no carry. It is related to the conditional control where we are going to check the carry flag value. Depending upon that, the control may be transferred to the label specified or subsequent instruction. The next instruction is JZ and JNZ, which is going to check the accumulator contents. So depending upon the instruction which you are using, either the control will be transferred to the label specified or subsequent instruction. Then we have the LCall instruction and ACall instruction. This LCall and ACall, it is used for calling a subroutine from one program to another program. The control will be transferred. So in the LCall or ACall, the address which you are going to be specified will be various. In LCall, the address of the subroutine from the main program, you can have 16-bit displacement. Whereas for ACall, it is only 11-bit displacement. So that should be reset within the 2K block. The next one is corresponding to the bit checking and followed by jump instruction with conditional checking, like JB, jump if bit set, jump if no bit. The next one is JBC, jump if bit set, and before going to the relative address, clear the particular bit. So these are the various instructions which are studied under this session, which are corresponding to the branch or control transfer instructions in 8051 microcontroller. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.